should start. Today, we are very happy to have Ofer Aharony from Weizmann Institute as the last speaker of our quantum space-time seminar series for this semester. And he's going to tell us about the derivation of AdS CFT for vector models. Over to you, Ofer.
Okay, thank you very much. I think this is already my second time giving a remote seminar in India, but I certainly hope that next time I will be able to come in person. And this will be a Blackboard talk, so I'll try to go slowly, and please do interrupt me with questions at any time. I mean, the price of having a Blackboard talk is that I won't be able to write long formulas, but hopefully this will enable more discussions. So this talk will be based on a paper that appeared last month in collaboration with our postdoc Shai and my student Erez Urbach. And the topic is a derivation of AdS CFT. So let's start by asking what does it actually mean to derive the AdS CFT correspondence. So the AdS CFT correspondence is a duality or an equivalence between theories of quantum gravity on anti-de Sitter space or on asymptotically anti-de Sitter space in d+1 dimensions. So we have some theory of quantum gravity living on this fluctuating space-time. And the AdS CFT correspondence tells us that this is the same as a conformal field theory in d dimensions, which lives on a space that's isomorphic to the boundary of this anti-de Sitter space. Now, this correspondence is best understood in the case where the gravity side is weakly coupled. So the limit where the gravity side is weakly coupled is famously related to the large unlimit on the conformal field theory side, and 1 over n plays the role of a coupling constant on the gravity side. There is also, of course, the opposite limit when the field theories are weakly coupled. That's, in some sense, when we understand the field theory side best. On the gravity side, because having a weakly coupled field theory means that we have some almost conserved high spin currents, which in the limit of a free field theory would be exactly conserved. This means that on the gravity side, in this limit, we have light high spin fields. So we're far from being in Einstein gravity, but we do still have some consistent theories of gravity. Now, what does it mean to derive a duality in general? Well, deriving a duality should be done either by sort of mapping directly the variables of one side to the variables of the other side and showing that they're exactly the same, or by proving that all the physical observables on one side are the same as all the physical observables on the other side. Now, for some 2D dualities, we can actually have 2D field theory dualities. We can actually have such derivations, but of course, in general, we don't really have such derivations for most of our favorite dualities, and the best we can do is just compute things on both sides to test dualities. And of course, we have lots of evidence for dualities, but we don't know really how to derive them. In the case of the AdS CFT correspondence, it's even less clear what it means to derive it, because if we're above in 3 dimensions or higher on the gravity side, and that's all that I'll be talking about in this talk, then these quantum gravity theories are not really well defined, so it's not even clear what the left-hand side of this correspondence means. So now, in some special cases, the left-hand side could be a string theory, and in that case, we do have at least a perturbative definition of the left-hand side, and then it is well defined to ask whether the perturbative expansion on the left-hand side is the same as the perturbative expansion in 1 over n on the right-hand side. And there's been lots of progress on testing dualities within perturbation theory. But if we're talking about a full derivation, then since we don't really have a non-perturbative formulation of string theory, it's not really clear what it would even mean to show that these two sides are the same. So in this situation, in some sense, the best that we can hope to do, since the conformal field theory side is well defined, at least for many conformal field theories that we know and love, then the best we can hope to do is to just map the variables on the conformal field theory side to the gravity side, namely to rewrite the conformal field theory as in a way that will make it look like a quantum gravity theory living on anti-de Sitter space. So that would be the best we can do in terms of constructing a derivation of the AdS CFT correspondence. Of course, in general, we expect that it would be very difficult to do this. We don't even know what are the right variables in which to describe these quantum gravity theories. We expect them to be non-local, to have extended objects like strings and so on. So it's not even clear what it means. But if we can construct such a mapping, then it would be very useful, because it would enable us to answer many questions that we don't know how to answer about quantum gravity. For instance, can we think of these quantum gravity theories in terms of a sum over metrics and topologies, or does that sort of description only emerge in the semi-classical limit and there's no full description of the theory in this language? This type of question could shed light, for instance, on whether we should include wormholes here on the left-hand side in the quantum gravity side or not. We could ask, is there a geometry behind black hole horizons? Even technical questions like how do we map, if we have in the CFT sources which take complex values instead of real values, how do we map them to the quantum gravity side? There are many questions about AdS CFT which we don't really know how to answer, and having any explicit mapping would enable us to at least attempt to answer these questions. So what I will describe today is our attempt to provide a derivation in the sense of mapping the right-hand side to the left-hand side, and what is probably the simplest case of the AdS CFT correspondence, namely the duality due to Klebanov and Polyakov between n free fields, which I'll take to be free complex fields, phi I of x, that I'll take to live on some Euclidean RD. And we're going to look at the UN invariant sector of this theory of n free fields. And that is believed to be dual to a high-spin gravity theory living on a d+1 dimensional anti-de Sitter space. And this example of the AdS CFT correspondence is the simplest one, since, of course, the left-hand side is as simple as it could possibly be. I mean, it's just a free field. We really know everything about them. And the right-hand side also becomes weakly coupled in the large unlimit. So, as usual, 1 over n is the coupling constant here on the right-hand side. So, in the large unlimit, both sides are classical or semi-classical, and we can really control everything about this correspondence. So if there's any chance of having a full derivation of AdS CFT, I think this is probably the best case to look for it. Now, of course, the disadvantage of this example is that it's very distant from the standard gravity theories that we're used to. In particular, on the right-hand side, we do have here massless high spin fields propagating on this AdS space. And the theory is non-local already at the anti-de Sitter scale and not just at the Planck scale. So this is very different from gravity in our world, but still it is a theory of gravity. And it would be nice if we could provide, at least in this example, a derivation of the AdS CFT correspondence. Now, about the right-hand side, in this case, very little is known. I mean, so there are classical equations of motion for these high-spin theories written by Vasiliev, but we don't have any way to do quantum computations on the right-hand side. We don't even have an action that would enable us to formulate what we mean by that, and even classical computations often run into divergences. So as an added bonus, of course, if we can derive the AdS CFT correspondence in this case, it would also give us a quantum consistent version of these high-spin gravity theories. So an automatic byproduct of deriving the AdS CFT correspondence in this case would be constructing a quantum version of these high-spin gravity theories that would make sense in terms of all quantum corrections. So my goal in this talk will be to show how we construct a mapping of this type, and in this sense derive the AdS CFT correspondence. So are there any questions about this introduction before I start? Okay, so there have been various attempts. Of course, this is not the first time that people try to derive the AdS CFT correspondence in this case. There have already been various attempts to derive it. Many of them tried to get the radial direction of AdS space from some sort of renormalization group direction. Now, in this talk, I won't discuss these other approaches. The approach that we'll take is really just a naive brute force approach, where we'll just take the path integral of our quantum field theory and just try to directly rewrite it as a path integral for fields living on anti-de Sitter space. And the formalism that goes behind this is what's been called bilocal holography, which was pioneered by Das and Jevicki already many years ago, and in particular we'll be following a paper from about 2 years ago by Mello Koch, Jevicki, Suzuki, and Yoon. So So the starting point for mapping the field theory to the gravity side in this case is to go to bilocal variables g x1, x2, which are just the UN invariant products of the fields at different points. So this is the sum over I goes from 1 to n. Again, phi I of x are these fields, then I goes from 1 to n. These observables, sorry, x1 and x2. So these observables are UN invariant, and in fact, if we're in flat space, then these are really the only UN invariant operators. All other UN invariant operators can be expressed in terms of these operators. Of course, this would not be true, say, if we're looking at SUN invariants, because then we'd also have baryon type operators and so on. But in the case of UN, these really form a basis for all the UN invariant operators. So the idea would be to first change variables to these bilocal variables, and then to express these bilocal variables in terms of fields living on de Sitter space. So our starting point is the path integral of our field theory. So we have this standard kinetic term for our fields, and we can imagine putting in some source for this bilocal operator. Of course, the bilocal operator, in the limit that the 2 points approach each other, we can expand this in a Taylor expansion and get all the local UN invariant operators, of course, which are usually discussed. And so if we put in a general source for this bilocal operator, then this would enable us to obtain all the UN invariant correlation functions. So our goal will be to take this path integral, which is our starting point, and to really rewrite it as a path integral over fields in AdS space. And so we'll do this in 3 steps. So this is basically the outline of the remainder of the talk. So our first step will be to carefully do this change of variables from our basic fields to these bilocal variables, gx1, x2, again defined by the top formula over there. As the second step, we'll take these bilocal fields and we'll expand them in irreducible representations of the conformal group. So of course, the free field theory in particular is invariant under Euclidean conformal group SO d plus 1, 1. And our basic fields are primary operators of this conformal algebra with the dimension of a free field, namely d minus 2 over 2. So this bilocal field transforms basically in the tensor product of 2 primary representations of this type, and then we can take that product and decompose it into irreducible representations of the conformal group. So, and then the coefficients of these representations will be our new variables. So they'll be written as some. Those representations will be labeled by some dimension delta, some spin j, and these indexes, and some point y in space. So our second step will be change of variables from these g's to the coefficients of the irreducible representations in the decomposition of this bilocal operator. And then as in the third step, we'll see that we can take these coefficients and reassemble them into fields living on AdS space. So we're going to have fields phi j living on AdS space of every spin j with some indices u1 up to mu j, and they'll be labeled by positions on AdS space. So as usual, I'll denote by z the radial coordinate of AdS, and of course they have a coordinate parallel to the boundary. And the nice thing about the mapping that we'll construct is that these last 2 steps will just be linear, namely we'll have a linear mapping between this bilocal operator in the field theory and these fields living on AdS space. Before I give the details, just schematically, you can easily see that a bilocal field like this has more or less the same number of degrees of freedom as spin j fields living on AdS space. You can identify the center of mass of these 2 points with this position x parallel to the boundary. You can think of the radial position is coming essentially from the distance between these 2 points. And then if you look at the angular variables in this separation x1 minus x2, you can expand those in spherical harmonics, and they give essentially the sum over the different spins of the fields in AdS. So just in terms of very naive counting, you can see that we do have more or less the same number of degrees of freedom in this bilocal and in the fields on AdS space, and we'll see that we can indeed map them from one to each other. So this is the outline for the rest of the talk. Will be to go over each of these 3 steps and see exactly how we do it. So are there any questions before I begin the first step?
Sorry, Ofer, what is the reason to expect that there will only be x and 1 additional variable from this type of mapping?
Yeah, so a priori there's no reason. I mean, it's sort of, but we'll see that these fields contain, I mean, can be expanded in exactly the same irreducible representations of the conformal group as those fields. I mean, of course, we expect to have variables living on AdS space because of conformal invariance as usual. I mean, our mapping will be manifestly conformally invariant, so we expect to have some SOD plus 1, isometry and so on. So it's natural to write things in terms of fields living on AdS space. And that's why we're adding just one more variable. I mean, of course, one could try also many other things. One could try to map it to bilocals on AdS space, and one could try many different things. But we'll see that this mapping does work. I mean, in the sense that we could really make it completely explicit.
Okay.
Ofer, Vasiliev's theory, as usually written, has a large number of auxiliary unphysical fields. Will you see any of that in your
yeah, so we'll discuss that more later, but the short answer is no, in the sense that, I mean, will these fields that will get an AdS will just be directly linearly mapped to those, so they will be well-defined gauge invariant objects and so on. And the field theory that we'll write for them, presumably the correct way to think of it is as some gauge fixed version of Vasiliev's theory, where you already got rid of most of the auxiliary fields and fixed a gauge for all the fields, basically, because all our fields are going to be gauge invariant and well-defined. But the assumption is that there is some way to gauge fix Vasiliev's theory to the theory of these fields that we're going to write down. But I mean, we do not know explicitly how to do that. But by construction, we're going to just work with physical fields, so no auxiliary fields and no gauge freedom on the AdS side.
Okay, thanks.
Any further questions? Okay, so the first part is to map these fields phi I to this bilocal field G. And now the problem with this mapping is that this part of the mapping is nonlinear. And these fields G, in general, obey various complicated constraints. I mean, for example, if we're in the simplest case, say, of n equals 1, then for n equals 1, it's obvious from this mapping, say, that the bilocal field obeys a constraint that says that gx1, x2 times gx3, x4 has to be the same as gx1, x4, gx2, x3 for any 4 points x1, x2, x3, x4. So G obeys this complicated constraint. For higher values of n, there are similar constraints on products of n plus 1 of these G's. So for any finite value of n, you do have very complicated constraints acting on the G's. So it's not so obvious how to build this mapping. In order to make it explicit, what we'll do is we'll put in UV and IR cutoffs on the field theory side by imagining that we have just a finite number of points in our field theory that are right is equal to V. So for instance, we can imagine just putting our field theory on a lattice and giving us UV cutoff and also putting in an IR cutoff that makes this lattice finite. So let's assume that we only have V points in our space-time. And of course, at the end, we can then remove both the UV and the IR cutoffs. So if we have just a finite number of points, then our field phi ix can be thought of as an n by V matrices, where the index I goes from 1 to n and x goes over these V different points. Well, this gx1, x2 can be thought of as a V by V Hermitian matrix. And of course, the mapping between them is just that this matrix G is 1 over n times phi dagger. And then the question is how to analyze mappings of this type. In particular, it's obvious from the form of this mapping that the rank of G is always going to be less than or equal to n. Again, if we think of it as a V by V matrix, and that summarizes many of the constraints that follow from this definition of the bilocal operator. So there are essentially two cases to consider. So the properties of this mapping vary depending on whether n here being the number of fields that we start from, whether it's bigger than V, the number of points in spacetime, or smaller than V. So we'll start from the case where n is bigger or equal to V. So we're mapping from the space phi I of x, which is a larger space, to this space G of V by V matrices. And in this case, it turns out that this mapping covers all of the space of G's. And so we don't have any, in this case, we don't really have any sharp constraints on the G's. And it's not difficult to even work out explicitly the Jacobian in this case for the mapping. So the Jacobian maps the path integral over all these fields phi I, where again, we have here now with this regularization, these are just n times v regular integrals. We map them to v squared regular integrals. And the Jacobian is simply the determinant of this matrix G raised to the power n minus v. So given this, we can just directly rewrite in this case where n is bigger than v. And of course, that's the case that's relevant for the large n limit, where we hope to get a semi-classical expansion on the gravity side. So in this case, we can just directly rewrite the path integral of the field theory that we started from on this other blackboard as an integral over these matrices G. So it's easy to rewrite the kinetic term for the scalar fields in terms of this variable G. It's essentially just two derivatives acting on G at the point where x is equal to y. It's, of course, our source term was already originally written in terms of G, so that's easy to translate to this bilocal language. And then the only other term that we get in the path integral is this determinant of G raised to the power n minus v, which as usual we can write as e to the n minus v times trace of the log of this matrix G. So again, as long as our regulator is finite and we have a finite v, then this is just some v by v matrix. And this is a completely explicit change of variables that we can make from our basic fields to these bilocal operators. And of course, the nice thing about this path integral that we get is that it is suitable for having a large n expansion, namely most of the terms here are just proportional to n, so it's obvious that 1 over n acts as a coupling constant for this theory of the bilocals, and the large n limit gives us a classical limit around which we can do a 1 over n quantum expansion. The only term that doesn't go like 1 over n is this term v, which one should think of as depending on the cutoff. I mean, it explicitly came from our UV cutoff and IR cutoff, and one should think of this term in the context of this large n expansion as a one-loop counter term, which has this very specific value v, and which is needed to cancel divergences that we would otherwise get when we do computations. So of course, by construction, this counter term has precisely the right value that's needed, such that the computations using these bilocals will reproduce for us exactly the same answers as the original field theory. So, so this is the situation when n is large, and in particular, we'll use this to derive a large n expansion of our theory. Yes, questions, please.
Yeah, I just wanted to ask about this change of variable. So when you make a change of variable from phi I of x, so that is like n times v variables, and you are going to g of x1, x2, which
that's
is
right.
Which is v times v variables. So that's v square variables. So that's a rectangular rectangular transformation. Is that right? So
that's right. So of course we're losing information while we're doing this, but we are keeping all the information about UN invariant combinations of the original fields. So these G's are UN invariant, and the claim is that these v squared variables do contain all the UN invariant information. So this is so in the space, in the UN invariant subspace, this is really a legitimate change of variables, and we can directly rewrite the path integral in this way.
I see. So I see. And this Jacobian is exact?
Yes, this is exact. Yes, it's easy to derive it. I mean, it basically just follows from scaling, I mean, from invariance and UN and all the different points in space-time are equivalent and so on. So that's very easy to derive. Yes.
I see. Thank you.
So this is the situation if we take this, in this case, that m is bigger than or equal than v. So again, the idea here is that we're taking the larger limit, and only after that taking the limit of taking our UV cutoff and IR cutoff to infinity. But that's of course a legitimate order of limits to work in, and in that order of limits, we get a usual large n expansion. If we want to analyze the other case of n less than v, so of course this case is also very interesting because that's the case that is relevant for finite n field theories. If we want to discuss those theories in the continuum limit, we have to deal with the situation of n less than v. In this case, they're much more complicated because our mapping in that case does not cover all the space of G's. In this case, we do have these complicated constraints on the G's, in particular on say of more than n plus 1 G's. We see that they're constrained. So in this case, we don't really.
Question, Ofer?
Yeah, sorry. Let me just finish the sentence. I'll answer a question. So, so in this case, the mapping does not cover the full space of G's. We have to implement these constraints. So in this case, we don't know how to make the change of variables so explicitly, but of course there is still some change of variables to the G variables and some action in the G variables that will be equivalent to our original action. But in this case, it is much more complicated because we do have to implement these constraints, and we don't really have a nice way to solve the constraints. So in this case, in this talk, I'll be focusing only on this case of taking the large limit and then thus deriving the perturbative expansion in 1 over n. But it is important that exactly the same change of variables does make sense also for finite n. Just the price one has to pay for working at finite n is that these G's obey very complicated constraints, but again, they're very explicit constraints that we can write down and explicitly. Yes, questions, please.
Hi, Ofer. I have a comment actually. One way of doing this is to introduce a delta function in the path integral involving this g of x file, and
yes,
then
exactly.
exponentiating the delta function in terms of a auxiliary, conjugate field.
Right,
and
exactly.
then, yes, but then, yeah, so then you can derive the whole thing very easily actually with a log determinant as a Jacobian and all that.
If n is bigger than b, then that is indeed a very simple way to derive this determinant.
Yeah, okay.
If it is smaller than b, then that doesn't help because you still have to implement all these constraints. But for n bigger than b, then indeed that's one very easy way to
That's right.
this Jacobian. That's right.
Thank you.
Ofer, question, please.
Yes.
So this n bigger than v limit, is it effectively equivalent to saying that you will not consider operators that are very big? So operators that have very many derivatives, derivatives that scale with n. When you
Well, it's not derivatives. It's this question of how many operators I have. So again, the constraints are in products of n plus 1 G's or more. So as long as I don't have a situation with more than n of these G operators, everything should be fine. But once I start dealing with n or more of these bilocals, then I run into trouble. Not a question of derivatives. Derivatives just go for the ride on both sides.
Well, I was thinking since you have only v space-time points, you can't take more than v derivatives.
Yeah, okay. Well, sorry, I thought you were talking about this other case when n is smaller than b. So here I can even take the continuum limit. I mean, so I can take this v to be very large and so on, and there should be no problem in taking the continuum limit, but I will have problems if I take more than n, a product of more than n fields, which of course is shown in gravity in many other places.
But in the case you're actually going to deal with, you're not allowed to take more derivatives than n, roughly speaking, right?
Yes, sure. In the order that I'm limited, that's right. Yes. So I'm taking n to infinity first, and only then removing the cutoffs in my computation. That's right. Yes.
Excellent. Yes.
Sorry, Ofer.
Yes.
In the case n is less than v, and you take v and n both to infinity later, what sort of large n limit would that be? What sort of operators would you be keeping more, or what are the relations that you are getting that you are not getting in this limit where n is taken large later? Right.
So I don't. Yeah, that's a very, very interesting question, but I don't really have anything smart to say about that limit. I mean, because clearly the constraints are still important. I mean, I do have many fewer variables than I would naively expect to have, but we don't really know how to take all these constraints into account. So so that would be very nice to answer, but I don't have anything smart to say about that. I'm afraid.
But just a quick comment. I mean, these relations are essentially the trace identities between the various operators.
Right. So here these are not trace identities, but these, I mean, in the case of adjuncts, these would be exactly the analog of the trace identities, right? These are those constraints.
Right, the fundamental, the phi by phi identities.
Exactly.
And these operate, so only the first n of these highest bin operators will be completely independent, and then there will be nonlinear relations.
You mean in this case of n smaller than v?
No, in the case n smaller than v, yes.
Yeah, so for n smaller than v, well, we have n times v independent variables. I mean, so n times v out of these v squared variables will be independent of each other, and the others will be constrained. I mean, but of course, the constraints are very complicated and nonlinear, so there's no nice way to solve for this n times v dimensional subspace of the space of all the v squared matrix.
Right, but I was thinking that if we just think of the operators in the CFT, the primary operators, there will be n independent primary sort of operators. Or at least some finite number of primary operators that are independent, and then there'll be nonlinear relations between them, coming from the usual analog of trace identities. And this will tell you that that the field space of all these high spin fields in the bulk has some complicated constraints involved.
Yes, that's right. But again,
no, I was asking.
It is better to look at the bilocal variables for this. And again, for the bilocals, this is the number of degrees of freedom that we have. And we do have n times v independent ones. If you look at the fields in all of space, I mean, we're going to get a very non-local theory. So I don't think you can just focus on local operators at one point. I mean, you do need to take into account the constraints in different points. But all in all, we do have n times v operators that are independent, and the other ones will be
Right. Yeah, because in both cases, you can take a large n limit. But I guess there's some non-locality in the second case, as you were saying.
That's right. I mean, so there's no reason why these order of two limits should compute with each other. And I don't think they do compute. Right. Definitely.
No, but you know, but it's not obvious to me that this is what we do when we actually start with the continuum theory and then take the large n limit. Why is it that the first case that we do?
Yes, I agree. But I mean, in our formalism, I mean, this is the only case we know how to do. I mean, so what I'm doing is definitely this case, and I'm saying that in this case, we will reproduce a semi-classical theory of gravity in the bulk. I mean, so my claim would be that this is the correct order of limits to take in order to really analyze semi-classical gravity, and that this is what we're implicitly doing when we discuss semi-classical gravity in the AdS CFT correspondence. But I don't, all the evidence that I have for this is just based on this simple example where, and this is how it works in this.
Thank you.
Any further questions?
So, Ofer, so does that mean then that in this particular limit, you cannot take 1 over n corrections in a way which would agree with your normal quantum gravity 1 over n corrections? I mean,
perturbatively in 1 over n, there's no problem. I mean, I can use this expansion. I mean, for n bigger than v, I wouldn't see this.
Yes, you will have a particular 1 over n expansion here, but this 1 over n expansion is different in some sense from the 1 over n expansion you would get from the in some sense the continuum Vasiliev theory, or I'm a little confused because it seems as if you cannot go to sort of finite n without sort of also putting it also on a lattice and so on. So would there be 2 different 1 over n?
Yeah, so this is a confusing issue indeed, and I don't have much more to say about it. But I mean, my point of view is that the Vasiliev theory should be thought of in this limit of first taking n to infinity and only then taking v to infinity. I mean, that's the limit where we can get semi-classical gravity, and we will get it. Well, in the other limit, I mean, we won't get, in any other limit, we do not get local, I mean, we do not get any gravity fields that are not constrained in the bulk. I mean, so if you want to have anything that looks like a 1 over n expansion of unconstrained gravity fields, that's what we get in the first limit. And my claim is that that would be the way to get a quantum version of Vasiliev's theory, which is what I'll show in the rest of this talk. But I agree that the way we usually think about it, but I don't think it contradicts anything that we usually do. I mean, because usually we do take both limits, I mean, the continuum limit and the large n limit, and we're just not careful about the order in which we take them. And of course, we do have various divergences in any bulk computation, so we do have to put in cutoffs and be careful about which order of limits we do things. So my claim is that this is the correct order of limits if we actually want to do it to obtain a quantum version of Vasiliev's theory.
I mean, if I'm agnostic about, I mean, since no one knows what is the quantum version of Vasiliev's theory, and I'm agnostic about what that is, would you say that there are 2 possible 1 over n expansions, or is it that you expect the 1 over n, and maybe at finite n things are different, but you can expect maybe order by order in 1 over n, and that would they agree? I mean,
that's what Jakob was asking, I think, on whether there is a good 1 over n expansion in this case of taking both n and v to be large and then doing a 1 over n expansion, but it's not obvious to me if there is such an expansion. I mean, we were not able to find such an expansion. Maybe it exists, but that's not what we're doing. So I don't know the answer to that question.
Okay.
But it's possible that there is a different 1 over n expansion, which would correspond to this other order of limits. And of course, they would all be the same for any finite n and v, but it would be a different expansion of the same theory. It's plausible, but I don't know how to deal with that other limit.
So is it correct to say, Ofer, is it correct to say that for n greater than v, there is a saddle point around which you do the 1 over n expansion?
Yes.
And the other possibility of n less than v, there is no such saddle point.
Right. That's a very good comment. Right. I mean, if we try to take v larger, then you can also see that this term that I usually think of as a counter actually bigger than the classical action, and it's not even clear what's the correct order in which to perform computations. That's definitely correct.
Thank you.
Okay. So any further questions?
Sorry, so Ofer, just to perhaps draw on to Rajesh's point.
Yes.
I mean, if the question is, what is the quantum Vasiliev theory? And
yes.
if you define it saying that it is the finite end theory which is on the boundary, right, in the continuum,
Yes.
then this particular approach is not going to give you that quantum Vasiliev theory, because here in this approach you won't be able to.
Yeah. Well, again, in this approach, I can do that. It's just very complicated because I have these constraints and I don't.
No. I mean, by your approach, I mean n greater than v approach. By that particular choice, I mean.
That's right. I mean, but I will get, even on the first limit, I do get a quantum approach in the sense of 2 orders in perturbation theory. This will give me a perturbation definition of Vasiljev's theory. It's 2 orders in perturbation theory. But if I want to analyze non-perturbative finite n effects, then I have to resolve this constraint.
Thank you.
Exactly. Yeah. Okay, so if we want to analyze the large n limit, then indeed, as Spenta was saying, we can just notice that there is a saddle point of this integral. Of course, we have here a linear term in G, so the saddle point to expand in is not G equals 0, but we have to expand around the expectation value of G at large n. And of course, from the definition of G, it's obvious that because this G is just phi x1, phi x2, then it has an expectation value, which is just some number divided by x1 minus x2 to the power d minus 2, just the usual 2-point function of free fields in flat space. So this is, so of course, this is what we expect from the free field theory side, but we can also explicitly check that this is a saddle point of this integral. I mean, it solved the equations of motion to leading order in 1 over n. So this is the saddle point that we'll expand around. So what we'll do is we'll take our bilocal operator and we'll expand it around this saddle point. We'll expand it with a coefficient of 1 over squared n for convenience, and we'll call the deviations from the saddle point. I'll denote them by eta x1, x2, and then we just need to plug this into this path integral and see what into the action and see what we get. So the action that we get for the eta variable, and so to begin with, we have this first term that's linear in eta. And we can write that term actually as G0 minus 1 times eta. I mean, this G0, it's because it is just the Green's function for the Laplacian, so it's inverse in the sense of this of these V by V matrices is just the Laplacian operator. So one can show that this linear term can be just written as this trace of G minus 1 eta. And then we have these other terms which are the trace of the log of 1 plus 1 over. So here I'm just again expanding G around this classical solution. And the expansion takes this form, and we can then write it very explicitly. Of course, the linear term cancels between these 2 terms. I mean, that's what it means that we have a classical solution. And then we have some quadratic term in the etas, which looks like 2 Laplacians acting on these eta. Then we have some of our interaction terms, which are suppressed by appropriate powers of 1 over n. And so I normalize things so that the etas have a canonical kinetic term. And then all the interaction terms are explicitly suppressed by powers of n, and they look like this G minus 1 eta to the power n. And then we also have the counter terms, which are lower by 1 order of 1 over n from the analogous terms in the main action. So again, they can be just written very explicitly in this language. So in this language, we have an explicit action for these bilocal variables, which again, order by order in the 1 over n expansion, we expect to exactly agree with the free field theory, again, for this very specific value of the counter term. And indeed, one can check that any computation that I want to do in the original theory, I can reproduce it in the language of these bilocal variables. I mean, so for example, if I want to compute, say, the 2-point function of these etas, which would be like a 4-point function of the original scalar fields, then at leading order in perturbation theory, this would just be a propagator of this eta, which comes from here. So this would just be so this would be explicitly equal to G0 x1 x4 plus times G0 x2 x3. That's what you would get from inverting this kinetic term. Then at the next order in perturbation theory, we'd have a contribution from various one loop diagrams, and also from a counter term diagram. So these would be the contributions at order 1 over n, where here I have this 3rd order vertex and the 4th order vertex, and here I have this counter term, the quadratic counter term. And one can show very explicitly that all these diagrams exactly cancel each other. Of course, in the free field theory, we don't really have any 1 over n connections, at least not in connected Feynman diagrams, the leading order at 1 over n is all there is, and one can indeed explicitly check that all these corrections cancel each other. So we have this bilocal action that, at least in perturbation theory in 1 over n, is completely equivalent to our original action, and then all that's left is to map this bilocal action to the AdS side. So that's what I'll do next, but are there any questions before I start doing that? Okay, so now I want to take these bilocal fields, in particular this eta field, and map it to AdS space. And the question is, how should we do that mapping to AdS space, or should we even map to AdS space? I mean, since we want to eventually construct a quantum gravity theory, which naively shouldn't live on some fixed space-time. So of course, one thing we know is that we have the local operators in our CFT. So they're given by these products of phi I of x times j derivative acting on phi I of x. So these are the local spin j operators that we have that have a dimension d minus 2 plus j. And we certainly expect these local operators to map to some spin j fields, which should be massless high spin gravity fields living on AdS space. So the natural expectation is that our mapping should at least include these massless high spin fields in AdS space. What's left there is really which space these fields should live on. And we'll sort of take the most naive assumption that we can make, which is that to take these fields to live on a fixed AdS space-time. Now, of course, at first, that sounds like a very strange assumption to make if we want to get a theory of quantum gravity. Well, first of all, we'll see that it works in the sense that we can map our theory to a theory of fields living on a fixed AdS space-time. And it's also not quite as strange as it sounds, because if you think in the language of Vasiliev's theory, then Vasiliev's theory really has a huge gauge invariance. And in fact, that huge gauge invariance is enough if you want to always fix the metric to just be the metric of anti-de Sitter space. I mean, there is a formulation of Vasiliev's theory where the fields just live on a fixed AdS space. So it's not completely preposterous to imagine that the high spin fields can be written as just living on a fixed AdS space rather than on a fluctuating space-time. And so that is what we'll do. So what we'll do is, again, just by brute force, we'll construct a mapping between our fields eta, which are again these bilocal variables expanded around the saddle point that I discussed before, and these fields of spin j living on a fixed anti-de Sitter space-time. And so that will be our goal. And the main clue for constructing this mapping is that once we took our fields to live on a fixed AdS space, then we know exactly how both sides should transform under the conformal group SOD plus 1, 1. I mean, here it's just transform using the isometry of AdS space. And here, of course, we know how these objects transform under conformal transformations. So the way to do the mapping will be just to decompose both sides into irreducible representations of this group, and then to just identify the coefficients between the two sides. So let's start from doing that in the field theory for these bilocal operators. So here we just have to take, so this lives in the product of two conformal primary representations with this dimension delta 0, which is d minus 2 over 2. And it's known how to decompose products of this type into primaries of the conformal group. At least if delta 0 is in the principal series. So I remind you that there's a special role played by the principal series of representations of the conformal group, where the dimensions of operators are d over 2 plus is for some real s. And if this delta 0 was also in the principal series, then the product of two principal series can be decomposed as operators of any spin j, which have any dimension delta, which is also in the principal series. And the coefficients in that decomposition, so the basis of functions, if you want, that we get from this decomposition are nothing but the 3-point functions of two operators of dimension delta 0 and one operator of a dimension delta in spin j. So so very explicitly, we can write this decomposition into primaries in the following form. So we have a sum over all the j's that appear in this product of representation and an integral over the principal series over this dimension delta of the operators that we get. Then we have an integral over an extra variable y. And then the basis of functions that we expand in, which transform as conformal primaries, are just these 3-point functions of two operators of a dimension delta 0 at the points x1 and x2 times an operator of a dimension delta in spin j with some indices mu I up to mu j sitting at this auxiliary point y if you want. So this is the basis that we expand in, and we're just going to call the coefficients of the expansion in this basis of, again, this is just the basis of irreducible representations of the conformal group. And we're going to call the coefficients of this basis, I'm going to denote them by C delta J of Y. So again, the claim is that these 3-point functions, when delta goes over the principal series and J goes over all the integers, are a basis for all functions of 2 variables. This is a basis that has nice transformation properties under the conformal group. And these coefficients are the coefficients of the expansion of my bilocal field in this basis. So this is just a standard conformal analysis. And of course, an important point is that this basis is a complete basis. I mean, so that we can also invert this mapping. So we can think of this as a mapping from the Erez, the bilocal fields, to these coefficients C delta J of the irreducible representation. And this mapping is invertible. I mean, so we can explicitly write also an equation for the C's. So there's going to be some coefficient and delta J, but we can also write down explicitly a formula for these C's as a function of eta, where the coefficients are again just going to be 3-point functions, but now with what are called the shadow representations, so d minus delta 0 of dimension d minus delta 0 and d minus delta at y. So we have this very explicit mapping between our fields eta and these irreducible representations C and their coefficients C delta J. So this is an explicit linear mapping. So here we don't have any problem with the Jacobian, of course. I mean, there is a small subtlety that the specific delta 0 that we choose is not on the principal series. I mean, it's moved slightly away from the principal series. So we do have to be a bit careful about analytically continuing the results about these decompositions from the principal series to our value of delta 0. But we did that carefully in the paper, and the result is essentially the same, except that in some cases, we need to slightly shift this integration contour over delta to a different contour, but that's more or less a technical detail. So up to these subtleties, we can just rewrite now our action for the AdS. We can just explicitly write it as an action for now these C delta J's, which are, again, just the expansion of eta in this conformal basis. So for example, if we look at the quadratic term in the AdS, so the quadratic term in the AdS takes the following form. Again, it has this integral with some constants. So of course, the action is going to be, of course, our original action was already very non-local in these bilocal variables, and also the action is going to still be non-local in these variables C delta J of Y. So we have C delta J of Y, C delta J of Y prime, and the coefficients of the quadratic term are just going to be the 2-point functions essentially O delta J of Y, O delta J of Y prime, and suppressing here all the various indexes that come with each one of those. So we have this simple quadratic term, and then of course we can also write down all the interaction terms just by using this again, just plugging in this decomposition into our action just written here on this other blackboard. So this is the second step, I mean, where we change variables from eta to these coefficients C. So are there any questions about this step?
So sorry, Ofer, I'm just a stupid question. So these C's, this is just is it? I mean, these are all 3 primaries, right? And so this is the thing that would be normally what you would fix by conformal word identities. There would be a fixed number of tensor structures and so on. Is that what the C is?
Well, no, sorry. I mean, the C's are the coefficients. I mean, of this decomposition. I mean, so again, we're decomposing the product of 2 representations of a dimension delta 0. We're decomposing that into irreducible representations of the conformal group. You should think of these 3-point functions. They're sort of the Krebs-Gordon coefficients of this decomposition of the product of 2 primaries into a third primary, and then the C's are just the coefficients of the functions that appear in this decomposition. So these are the coefficients of these different elements.
So that brackets is not some field theory correlator or anything.
Yeah, sorry, right. Sorry for not being clear. Yeah, so these are not operators in any specific field theory. This is just a notation for just the abstract 3-point function in a CFT. Operators dimensions. Of course, these are scalars, and this is the spin J operator. So this is just some uniquely determined 3-point function, I mean, which we can normalize to have coefficient 1 in an appropriate sense. And then these C's are the coefficients of that. Right. So these should not be confused with any physical operators in our theory. These are just the abstract 3-point functions viewed as just as Krebs-Gordon coefficients for the products of representations of the conformal group.
Okay, thanks.
Any further questions? Okay, so the final step is now to go to the bulk and just try to write down a similar decomposition for the bulk fields. And so we want to have these fields phi j in the bulk with indices mu1 to mu_j. And it turns out that if we want to have a similar decomposition with exactly the same representations appearing, then we need to take these fields phi j to be symmetric, only in symmetric traceless combinations of their indices. And also we need to take them to be transverse. So our fields by construction will obey a sort of a transversality constraint that for j bigger or equal than 1, that d mu1 times phi j mu1 is equal to 0. So you can think of this. So if these phi j's would have come from some gauge field on the bulk, you can think of this as some gauge fixing condition. But again, for us, we do not see this this gauge invariant formalism. We just see the physical fields, and the claim is that the physical fields that we find obey this constraint. And then the claim is that these fields phi j obeying this transversality constraint can be decomposed into precisely the same irreducible representations of the conformal group, where now the basis elements, or if you want the club squared out coefficients, these basis elements are not the 3-point functions, but they're just bulk to boundary propagators in AdS space. So now we're going to have coefficients which again are labeled by delta and j, and by these combinations, say mu1 of 2 nu_j of some y, and the basis elements that we're now expanding in order to get an irreducible representation of this bulk field, decomposition of this bulk field into irreducible representations of the conformal group. Then the objects that transform in these irreducible representations are just these bulk to boundary propagators that have two sets of indices between some bulk point labeled by x and z and some boundary point y in anti-de Sitter space. So these g's are the usual bulk to boundary propagators, which are defined such that they obey a Laplace equation in AdS with an appropriate mass, which is the usual mass related to the dimension delta, namely delta minus d minus j, and of course they obey also the appropriate boundary conditions and so on, which I won't write down explicitly. So we have explicit formulas for all these bulk to boundary propagators. They are, and the claim is that these are a complete basis for these transverse functions in AdS space. And if we expand these bulk fields in these functions, then our coefficients are labeled by exactly the same parameters that we found in the field theory by expanding the bilocal field. So we have exactly the same coefficients, or exactly the same number of coefficients C delta, which are again labeled by this dimension delta, the spin j, and the position y, which in this case we can think of as the position on the boundary of AdS space, but of course it's the same as some coordinate in the quantum field theory. So this is our decomposition on the bulk side. And now once we have this decomposition of phi into the C tildes, and we had this other decomposition of eta into C's, then the natural mapping to construct between the two sides would just be to identify these C deltas with the C's that we had in our expansion of the field theory side. Now this would be nice, but unfortunately, this is not uniquely determined by the conformal symmetry. I mean, so of course, conformal symmetry tells us that we should map the coefficients of some dimension delta and spin j on one side to the coefficients of the same representation on the other side. But the mapping between them could involve some arbitrary coefficient f delta j, which could depend on delta and j. Any mapping of this type would still be consistent with the conformal group. So just by conformal invariance, we cannot determine these coefficients f delta j in the mapping. But for any choice of these f delta j's, this relation gives us a very explicit mapping between our bilocal variables and the fields that we have in the bulk. And of course, we expect to get this freedom because a priori nobody told us which field we're supposed to use in the bulk. I mean, we could use phi, we could use a box phi, we could use any other field redefinition in the bulk. We have obviously huge freedom to make, and that freedom is embodied in our discussion in the form of these coefficients f delta j, which are a priori arbitrary. But for any choice of these coefficients, we get a very explicit mapping, and let me just write it down in full glory. So the expansion in full glory is just given by these expressions. I mean, so the first line tells us how we map a bilocal eta in the field theory to the value of the field phi j in the bulk, where again, we have here this f appearing, and otherwise, these are just these bulk to boundary propagators and these 3-point functions. So these are just explicitly known functions. And the only subtle part is that it involves this integration over the dimension delta in the middle, but in principle, this is just a well-defined function. And similarly, the fields in the bulk can be mapped to the bilocal by just the inverse of this relation, which again takes this following form, which is explicit but somewhat complicated. So this is our mapping from the bilocal variables to the bulk fields. So are there any questions about this?
Ofer, in the last formula, the y integral can be done, and is the kernel still simple?
Well, it can't really be done explicitly. I mean, we won't be able to do it explicitly in terms of elementary functions. I mean, yeah, of course, in principle, all the integrals can be done, but I mean, we couldn't find a simpler form than the one that I wrote.
So,
the y was in the frequent function and in the bulk to boundary propagator. I mean, so it's some sort of a convolution of a frequent function in the CFT with a bulk to boundary propagator in AdS. Right. I don't know any simple expressions for that, and if there is any
geometric function,
hear about them.
Sorry, that formula again, the last formula.
Yeah.
There's an integral over delta, right?
That's right.
So does the integrand, like these f delta j, n delta j, they have poles such that this picks up essentially the delta corresponding to the field on the right-hand side, left-hand side? Is that?
Yeah, okay, so that's right. So that's an excellent question. So not directly here, but what you expect, and indeed what happens, is that if you don't look at eta, but if you look at some local operators, so if you then try to compute some correlation function of local operators, so look at the limit where these 2 points approach each other, and look at the limit of some correlation function of these local operators, then in the computation of these local operators, then this integrand indeed exactly has poles in the delta plane corresponding to the physical dimensions of that you expect for the dual operators, and indeed it gets contributions precisely from those values. But that only shows up again when you look at local operators and you look at their on-shell correlation functions. I mean, it's not an exact relation, but in any specific computation of some on-shell correlation function of the local operators, then indeed that's exactly what will happen. And you can close the contours here and compute these integrals by getting the coefficients of these poles. That's right.
Okay.
Now, in general, we can now take this mapping and use it to just map our action in data variables to an action for the bulk variables. Now, of course, this action in general is very complicated and certainly non-local. But one way in which we can fix this freedom of field redefinitions is to require that this bulk action is as local as possible, at least for the quadratic term. I mean, so the higher interaction terms are always very non-local, but we can make a specific choice of this f delta j that makes the quadratic term at least as local as possible. So we have some explicit choice that it's not too illuminating, but I'll write it down here. Unfortunately, the specific choice is not an analytic function of delta, but it has branch cuts. So one has to be a bit careful in doing analytic continuations, and we try to be careful in our paper. But anyway, there's some very specific choice of delta, which happens to take this form. And if we take this form, then the quadratic action for the phi j's at least turns out to be local. So with this form, then the quadratic terms in the action that we get in the bulk just look like a local differential operator acting on these fields phi j, where the only non-standard thing is that we get an operator that's quartic in derivatives instead of quadratic. So we have an action in the bulk in this case, which is local, but it's fourth order in derivatives instead of second order in derivatives. Of course, for general f's, what we get is completely non-local, but the best we can do is for the specific f to write the action in this specific way. Now you'll notice that this quartic operator derivatives is just a product of two quadratic operators. I mean, this operator is sort of the quadratic operator that we expected to get in the bulk. I mean, this is exactly what would give us the propagator of the physical bulk fields, which are these massless spin J fields that have dimension delta plus J minus 2. But it looks like together with them, we get some extra unphysical fields, even in this simplest choice of F, which would have some dimension D plus J, and which would, if you compute their propagator, they would actually have a negative propagator. If you invert this quartic operator, they would actually have a negative propagator. So we also get these unphysical fields. But I mean, of course, the important thing is that we do see the right physical fields, but we do happen to get also these unphysical fields. Now, these unphysical fields actually almost map with some ghost fields that you would get from Vasiliev's action. So it turns out that if you take Vasiliev's action, so of course you start from many more variables with lots of gauge fields and auxiliary fields and so on, but there's some specific gauge fixing of Vasiliev's theory that you can do, where you would have exactly these physical fields and ghost fields that exactly match these fields that we get here. So one possible interpretation of these fields are that there are some remnants, ghost remnants from some gauge fixing that we would do. But again, that's just at the level of speculations. So this is the form of the quadratic action, and let me just show also the form of higher order terms. I mean, so we do have explicit formulas for the full action for the bulk fields, but of course the general action is very complicated, but it is explicit. So for example, if you want to ask about the first interaction term of three bulk fields, then it takes this form. So we have here this product of three of these fields, phi j's, with different spins in the bulk. And then there's integration over their positions, but there are also integrations over these extra variables, dimensions and y's, and also three extra bulk points on the boundary. And these coefficients are given by these very specific convolutions of bulk to boundary propagators and 3-point functions. And of course, it's a highly non-local interaction, as of course we expect in the first place, since we expect this to be a non-local theory in the bulk, and we do find this type of non-local interaction.
Sorry, of question, please, Ofer.
Yes.
If we were interested, let's say I was interested in the phase space of my bulk theory at linear order. So just the path that comes from the quadratic action.
Yes.
So are these funny guys part of your phase space?
Yeah, so that's a question. So to ask that, so I didn't emphasize this, but perhaps that all the mapping that we did so far is just in Euclidean space. And I think that to answer your question, we have to generalize our mapping to Lorentzian space, which is something that we're working on now. And it would be very interesting to see what we would get in Lorentzian space. And of course, we do know, for instance, if we were looking at the CFT, say on a d-dimensional sphere, then we know that the physical operators that give us the spectrum of physical states on the sphere would only involve these operators, and they would not involve these other operators. So these other operators had better drop out somehow if we would try to compute the theory on a sphere, say on a sphere times Lorentzian time or something like that, and they should not be in the Hilbert space. But that's something that we're working on now to verify that that's indeed the case. But so far, everything that we did is Euclidean, and in Euclidean space, I mean, a priori, we don't see any big difference. As far as the bulk action goes, I mean, these fields appear at the same footing as these other fields. Of course, when you compute correlation functions, I mean, of the local operators, then the contributions from these physical fields will dominate. So on the on-shell, we'll just reproduce the usual finite diagrams that you would write down in Vasiliev's theory, basically, that just involve these physical fields. But certainly when you compute loops and so on, then these unphysical fields would also contribute.
I see. Going to Lorentzian space is not just analytic continuation.
Well, it's very subtle to do in general in conformal groups and so on. And so, yeah, we don't know yet exactly how to do it. I mean, it will be some sort of analytic continuation, but exactly which one? I mean, there are lots of contours here to integrate over that we have to carefully rotate and so on. I mean, so I don't know yet what to do about the Lorentzian theory.
Okay, thanks. I was thinking just global time and AdS, if you analytically continue that in your bulk action. That's not the right thing.
Again, what we did is for RD. I mean, so it's for the Poincare patch, not for, So, and then the Poincare patch, it's more difficult to ask the good questions and so on. So, yeah, so they're all very good questions, but we're working on analyzing them. But so far, that's all that we have. But again, so just to summarize, so what we have is we do have an explicit action for the bulk fields. And this action, by construction, it reproduces for us exactly the correlation functions of the field theory. I mean, so using this action and these complicated vertices, in principle, we can compute any correlation function of the Erez that we want. And so we can compute it classically and also quantum mechanically. We can compute the loop diagrams. And we do get, when we include the appropriate counterterms, which we also map from the field theory, we do find exact cancellations of all the vertices that we would get in the bulk and so on. I mean, so we do have a well-defined quantum action with the disadvantage that it's highly non-local, but it is a completely explicit action that you can write down on AdS space, which again, by construction, reproduces for us exactly the correlation functions of the free CFT. And in particular, we can also use this action now. So if you want, we can take limits where we could compute the correlation functions of local operators like AdX and compare those to the similar expressions in the field theory and so on.
Say, supposing you took the spin 2 field, is this quadratic piece like the linearized Weil tensor? square? I mean, is it like the linearized wild type square type of action?
So this piece, well, it's the only quadratic term you could write down for a traceless transverse graviton living on a fixed AdS space. So
it's presumably the wild tensor square of the say linearized about AdS background.
Right. Yeah. So I think you think about basically has to be since it follows from the symmetries of the problem. So yeah. So you can probably think of this as some gauge fixing of the metric to be to obey. So again, all our fields do obey this constraint. So say the spin 2 field does obey this extra transversality constraint that you can always impose, and with that constraint, then this is basically the only quadratic term that you can write down. And so that's what you get the same propagator as for a graviton expanded around a fixed AdS space.
Right, but then it would suggest that even in the Euclidean signature, this is essentially something that starts with the Weil square and then has corrections. So it sort of is it? I'm just trying to think whether where do you? I mean, so there's no Einstein-Hilbert term at all in some sense.
I think that also the Einstein-Hilbert term, if you would expand it, I mean, in this sort of gauge, I mean, on a fixed AdS space, you would also get. I think you'll get the same thing. I don't think it's only the. I don't see why it's only the wild component.
I think Rajesh is asking about the combined quadratic term with the fourth order thing, the product of the term.
Yeah. Okay. Yeah. Okay. That's possible. Right. Yeah. So that I haven't thought of. I mean, so for that you have to add some extra fields on top of the original one, and yeah. So I mean, of course, it's possible that it's related to conformal gravity or something like that. But I mean, I really don't know. I mean, again, it's difficult to ask these questions because we only see this gauge fixed formalism, where we really only see these specific modes that are physical by themselves, and it would be very nice to sort of ungauge fix this and write this in a covariant language with the gauge symmetries that we expect these spin J particles to have, but that's not what we did so far. I mean, so for now we just have this action in these gauge fix.
But at the quadratic order, you can presumably do it, I mean, field by field, and therefore you can just gauge fix these, I mean, just impose some transverse gauge for the graviton and then and try to compare it with a gauge fix version of into action. I mean,
yes.
so you can write down a dispersion relation, which is what you have, and try to see what kind of quadratic piece that is.
Right. So we haven't tried to do that for the Weil square term. I mean, so we tend to think of these other fields more as ghosts, but yeah, but it's possible that also some natural.
The Weil square term does have ghosts, so that's why I was asking, because for the same reason, like Shiraz said, I mean, in the phase space you have these because it's a fourth derivative term. It does have these ghosts. I was wondering whether it's the same ghost, the same. Thing.
Right. Okay. Yeah. So we haven't checked that. So yeah, that's a good question. So yeah, we should maybe check if it comes from this simple form. Yeah. So we haven't checked that. So I don't know. So yeah. So this is basically it. I mean, so again, using this action, we can compute correlation functions as much as we want. We can also analyze the deformations of the theory. So again, since we have an explicit mapping in the path integral, then any deformation that we do in the field theory, we can also do the same deformation in our path integral of the fields in anti-de Sitter space and see exactly its effect. And so in particular, of course, one interesting deformation to do would be just add the phi to the fourth term, which in our language is essentially just this integral over xx squared. So we can deform the theory by this. So this maps to some quadratic expansion in the scalar field that we have in the bulk. And so we can explicitly map this deformation to a change to a deformation in the quadratic action for a field phi 0 in the bulk. And then if we want, we can take the limit of lambda goes to infinity to go to the critical theory. And more or less, as you would expect, I mean, then even though this phi 0 has a quartic action, then basically the effect of this deformation, just like in the usual AdS CFT correspondence, is just to change the boundary conditions for this field in AdS from the boundary conditions where it would have an operator of dimension d-2 to the propagator, where it would look like an operator of dimension 2, as we expect in the critical theory. I mean, so all these things we can explicitly do. Of course, in the free field theory, we expect that all the loops in the bulk should manifestly cancel each other, because we know that there are no corrections in the field theory. But in the critical theory, once we have this deformed propagator, then the loops are not supposed to cancel, and they're supposed to explicitly give us, well, by construction, they explicitly give us all the 1/n corrections of the critical UN model or the critical ON model. So essentially, we can now rewrite all these corrections as loop diagrams in AdS space in this high spin theory, and our construction guarantees that these loop diagrams give us precisely the correct answer. So I see that I'm out of time, so that we summarize, but are there any questions before I summarize?
So Ofer, one question. So
yes,
this particular map involves a lot of kinematics also, right? I mean, the fact that you are taking the two representation, decomposing into these irreducible representations, and using the bulk boundary propagator to map it to the bulk degree of freedom. So I wonder whether you know, one could treat strongly coupled gauge theories also in this way, where you have two operators joined by a Wilson line, and then do similar type of a kinematical change of variables to get to the variables of gravity theory.
Yeah. So that's a very interesting question. I mean, it's one of the directions we want to pursue. I mean, I doubt if you can, for matrix theories, if you try to do it for matrix models, then you'd get stuck already in the first step, that we don't know how to do this change of variables in the field theory to these gauge invariant variables. But if you want to do it to vector models coupled to gauge fields, then in principle, as you said, you can do it by inserting Wilson lines, and indeed that's one of the directions we'd like to continue in. But for matrix models, already the first step is much more complicated. Of course, we don't know how to map the space of fields to the space of all gauge invariant operators. There are complicated constraints between them. We don't know how to do anything analogous to that. Any further questions? Okay, so let me just summarize. I mean, so we wrote down an explicit but non-local mapping between the UN invariant operators in the field theory, as summarized in this bilocal field at x1, x2, to bulk fields phi j living on a fixed AdS space, and we wrote down an explicit action for these phi j's. As I said, we expect this action that we got for the phi j's to be some gauge fixed version of Vasiliev's theory. And it would be very nice to check that explicitly. I mean, I'm not an expert on Vasiliev's equations of motion, but in principle, we believe that there should be some way to gauge fix Vasiliev's classical equations of motion, such that they will give us precisely the equations of motion that we find for our fields phi j. I mean, but I don't know exactly which gauge fixing it would be. Again, you have to formulate Vasiliev's theory first on a fixed AdS background, so that was done, but then you have to analyze the equations of motion and that formalism and find some gauge fixing that would give this. So that's one thing that remains to be done. Or of course, you could try to go in the opposite direction and try to ungauge fix what we found and write down some gauge theory, any gauge theory whose gauge fixing would give the action that we got there. But so far, we don't know how to do that. I mean, so this is in the context of the large N expansion. And in this context, again, we could also study deformations. I mentioned the deformation to the critical theory. You can do a mass deformation and find exactly the gravity dual that's dual to the mass deformation, so to the massive free fields. I mean, so of course, in our formalism, the fields still live on AdS space, even when we discuss the massive theory, but the scalar fields would have some profile in the bulk if we want to describe the massive theory. And any other deformation we can also easily study in our formalism. For finite N, then again, we should be able to perform an analogous mapping to the phi j's also in that case. But we see that in that case, we get these complicated constraints. I mean, so the constraints on the product of n+1 of these bilocals translated to constraints on a product of n+1 of these gravity fields. So we have constraints on products of n+1 gravity fields or more, which are horrible non-local constraints in the language of these phi j's. So it's not so clear how to implement them. I mean, our takeaway message from this is that probably these gravity fields are not really a useful language in which to describe the bulk at finite N, because they obey such complicated constraints. So probably I would say that gravity really only emerges as a useful concept in this 1/n expansion. Well, for finite N, it doesn't really seem to be very useful. But perhaps there is some way to construct some other large N expansion which would also include these constraints, and that would include some gravity variables that would be useful also at finite N. But that remains to be done. There are many future directions to continue in. So I already mentioned some of them in the talk. One obvious generalization is the generalization of this to free fermions instead of free scalars, which we're trying to do. Another obvious generalization is to look at other manifolds. I just worked on flat Euclidean space. One can look at the theory on a sphere and various other manifolds. Of course, if we look at manifolds that include time, I mean, so let's say if we want to put the theory on SD minus 1 plus S1, then it's already much more complicated, because in this case, if I want to really implement consistently the truncation to UN singlets, then I would have to couple the theory to UN gauge fields, and I would have to add UN holonomies on this circle. So in this case, it's not too obvious how to generalize the analysis to this case. I mean, so the analysis in the way that I present it is very much tied to the fact that we don't have any non-trivial cycles, and in the presence of any cycles, it's not too obvious how to generalize this. Another generalization that I already mentioned is to the Lorentzian theory, and in particular, in the Lorentzian theory, we could ask about black holes. I mean, so we could construct finite energy states of the free field theory, map them to the bulk, and then build a black hole background and ask various questions about those backgrounds, again, in the context of these non-local high-spin gravity theories, but still, they should have some black hole solutions, and it would be interesting to analyze their properties. One could also try to play similar games for the DS CFT correspondence for vector models, and in principle, we could also try to play similar games there. And well, of course, the most interesting question is what, if any, of this whole story can we take away to more complicated examples of the AdS CFT correspondence, like the matrix models or anything? So do the qualitative properties that I described carry over also to that case or not? But on that, unfortunately, I don't have anything concrete to say. So thank you very much.
Thank you very much, Ofer, for a very nice talk. Let's please unmute and thank Ofer for the same. Questions?
May I ask a question? Ofer. So, as you know very well, that if you look at Chern-Simons theories with vector matter, they can also be written in terms of bilocal variables. So presumably this analysis of going over to a conformal basis might be useful there also.
That's right. So there we can also construct bilocal operators, but we have to add them with the Wilson line between them. So, and then there's some choices to think about.
We can fix a gauge. There's no Wilson line then. So it's exactly a bilocal theory.
Well, okay, it depends on the formula. If we want to do it in a manifest way, then we would have to include Wilson.
Yes.
Yeah, there are various gauges you can work in and so on. Try to simplify it, but that's right. I mean, so indeed, so I mean, everything that I talked so far was about general dimensions, but indeed in 3D we have this nice option of coupling the theory to U and K gauge fields, and we know from the dualities to Vasiliev theory that even on the field theory side, when we do this, we don't really add many degrees of freedom, and also on the gravity side, we believe that it's described by a very similar theory. So we have to be careful now about the gauge invariance of this UNK theory, but in principle, we believe that it should be possible to repeat everything that we did to this case. So this would be sort of the simplest generalization to an interacting theory, perhaps. And indeed, it would be very interesting to generalize to this case. That's right.
One comment, Ofer.
Yes.
So this kinematical factor that goes into this mapping, which is 2 boundary points to 1 bulk point, right?
Yes.
So I wonder whether using conformal Casimir equation, the way one fixes the conformal block, if one can fix this, factor.
You mean write it down? Write it down in a more explicit way than we did.
I mean, write down the solution to the
different explicit way than what's written up there. But I mean, possibly we didn't try too hard. And yes, it's. I mean, again, this is the. I mean, all of this does just follow from the analysis of the conformal group and the map and the decompositions of these two different objects into the same representations and so on. I mean, it would be very nice if one could perform some of these integrals explicitly and write down a more direct formula for this mapping. I mean, we weren't able to do this, but maybe it is possible, definitely.
So, Ofer,
what I discussed is that one has to be careful, of course, about this integral. This does go all the way to infinity, so one has to be careful also about various versions in these integrals, but we believe that one can't control them and that this really is a well-defined mapping. Yes.
Yeah. So, I mean, one particular 1/n correction, which is very robust and very sort of universal, is the one loop correction that you just get from the fields, just from the integrating out. And since one has this quadratic action at the, I mean, so it's only sensitive to the quadratic action. So the one loop determinant in some sense of this action, would it agree
Right.
with
so that's so that's one of the things that we're trying to do now. But yeah, the one loop determinant of this action is a priori quite different from the one loop determinants that people tried to analyze before, where they only had quadratic and derivative terms. So this would give us a different one loop determinant. Now, of course, if we really want to match the partition function of the theory on SD, then we have to also match the classical part. I mean, there is a classical contribution to this partition function, which we get from our mapping, and there is a one loop part. And I mean, if we do our mapping consistently on SD, then by construction, the one loop part would be the correct one to balance the classical terms that we get. So that's one of the things that we're trying to do now to really work this out properly. But I mean, this one loop correction will be different from the standard one that people compute. But I mean, there's also no reason why it should be the same, because I mean, it doesn't really make sense to compare one loop contributions if you don't know the classical contributions. And in the usual mapping to Vasiliev theories, nobody knows what's the classical contribution at order n already that you would get from the bulk. I mean, so in our framework, I mean, it will be possible to make this one loop contribution well-defined, in the sense that we'll have a well-defined classical contribution from the mapping and a well-defined one loop contribution. And together, of course, we're guaranteed by the construction that they'll give us the correct partition function. But for that, we still have to carefully do the mapping to SD. I mean, in principle, it's straightforward because it's just conformally related to flat space, but we're still working out on the full details of that.
Yeah, but I mean, I was just wondering whether it's related to this n greater than v or n less than v limits, because it is because the extensivity of the one loop determinant, that it is proportional to v.
Yes.
Would that probably doesn't happen here, right? I mean, that you get a free energy which is extensive. In this thing, it would be because the other one, that's what I think you get this log of the determinant, you get then this extensive free contribution to the free energy. So I'm, in fact, a lot of this thing reminds me of what Zeitlin and others have talked of as conformal higher spin gravity, which is sort of like a conformal extension of like this wild gravity or conformal gravity, because there you get these sort of I mean, I think there's the wild square piece, and then there are other pieces. So I was just wondering whether maybe there are two different gravity, and that has, again, I think Zeitlin and collaborators have looked at the one loop determinants of conformal higher spin gravities, and I was just wondering whether there's perhaps.
But it wasn't clear to me that I thought that theory didn't have the same physical fields as the usual high spin gravity, but does it?
I mean, I think it would be the same physical fields, but it would be sort of having this.
Yeah, okay. So
gravity would be having a Weil kinetic action rather than a Einstein-Hilbert kinetic action. But I think there's probably some. Okay, I'm not an expert on that theory, but I mean, I've not studied it or anything. But it sounded or it smelt a little like that because it would seem. Yeah. But anyway, it's
yeah. I'm familiar with it. We'll definitely have a look at that and see if
because the one loop determinants there that Zeitlin and others computed were of things involving quartic terms, if I'm not mistaken.
Yeah, so we'll definitely have a look at that and see. I mean, yeah, I don't know the answer to that. I mean, but I don't think this is related to this question of n versus v. I mean, of course, this v, when you compute the partition function on SD, then of course you have the UV divergences and so on, and the first are proportional to the volume and so on. So that's essentially our constant v. I mean, but the thing we're interested in is, of course, not these pieces, but the finite pieces that remain. I mean, if you're in odd dimensions, what we're interested in is the piece that remains after we throw away all these pieces that depend on the UV cutoff, and those pieces are supposed to match between the two sides, and so So we should, so in our formalism, I think even for finite V, I mean, we will have these pieces that will depend on V, and which will be these V divergent contributions to the partition function. But the interesting pieces are the finite pieces, and those again, by construction, they should match between the two sides for us. I mean, I didn't mention explicitly, I mean, of course, in the field theory, I discussed the specific lattice regularization. I mean, in the bulk, of course, we don't use this lattice regularization. So in the bulk, if you want to do computations, typically we would use some other regularization, like putting in some cutoff on the radial direction and also some IR cutoff on this space X. And but in any regularization that we use, then we're going to have some specific counter terms whose value depends on the regularization we use, and we can explicitly compute them and use them to show that all the divergences that cancel in the same way as they do in the field theory. So of course, to explicitly do computations, we're not using the specific lattice regularization in the bulk. We'd be using some other regularization, but of course, the final answer is again in this formalism where we first take n to infinity and then take the regulator away. We do get for any regulator, we get finite answers that reproduce for us the field theory results.
Over a question, please.
Yeah.
Suppose you were to do the following field redefinition. So for the formula that's sort of behind you with the fourth order kinetic term, suppose you were to do the field redefinition psi is equal to square root of del square minus m, you know, the term you don't want, square root of del square minus m times phi. That would then make the kinetic term what you wanted. Is there some reason not to do that?
Yes. Yes, there is. I mean, because so if you try to do that in this brute force way, then you would get singularities in some of the other interaction terms. I mean, so you would get, so your change of variables would involve the square root, and that would give extra unwanted sort of singularities in the form of the other terms. But it turns out that you can, in a non-singular way, sort of shift this mass to be at some other values of the mass. So that you can do, but if you want to completely get rid of it, then it would make the other terms in the action singular. So that when we tried to do that, but yeah, we weren't able to do that without introducing extra singularities. But it is possible to play around with the mass of these unphysical states, and that you can do without introducing extra singularities. And we don't really know what's the interpretation.
Okay, one more question, please. In your change of variables, you had a nonlinear change at some point, and then you had various linear changes of variables. And did you keep careful track of the determinants of the linear changes of variables as well through your program?
Well, for flat space, we didn't need to do it because they're just constants that would sit outside the action. I mean, our main difficulties in doing the sphere case is that in the sphere case, indeed, we do need to keep also all these Jacobians as well, because we do want to keep the finite piece eventually of the path integral. So for the sphere, these are meaningful, and we do plan to keep track of them consistently. But in flat space, these are just constants that are independent of the field configuration, and so they just sit outside the whole path integral, and we don't really care about them.
Okay, so either for the sphere or for s d minus 1 times time, I was wondering whether some of those Jacobians would cancel the determinant you got from the unphysical poles in your fourth order action.
Right. So yeah. So there are going to be cancellations between various things, but right. And so we have contribution from the Jacobian, this first order thing, from the classical actions, and so on. And so there are lots of moving pieces around, but eventually they'll all be canceled.
Right. Okay. Thanks.
Correct.
Ofer, can I ask a question?
Sure.
So maybe you have already mentioned during the talk, but I may have missed. Can this be applied to 0 plus 1 dimensional theories like the SYK?
Yeah, so that's a very good question, and that's also one of the So that's also one of the things that we're doing in the future directions is indeed to do it just for 0 plus 1 dimensions. And so everything that I did was for 2 plus 1 dimensions or higher. In 1 plus 1 dimensions, this mapping that I described doesn't really make sense because scalar fields are not primaries in 1 plus 1 dimensions, so that case isn't part of this formalism. But 0 plus 1 dimensions we can do, of course. In that case, also, I mean, free scalars have negative dimensions and so on, so it's not a completely standard case. But we can repeat our formalism also for this case, and that's one of the things that we're also trying to do now. In this case, we have fewer fields in the bulk, so it becomes simpler. And we hope that at least in this case, we can make the mapping more explicit. So indeed, that's one of the things we're trying to do now.
So whatever is known about the SYK model and this bulk dual can be understood in that way as well. I mean,
well, I'm not sure how similar this will be to what arises. I mean, yes, of course, there are going to be some similarities to what happens in SYK. I mean, yes, well, certainly if we do it for fermion, but also when we do it for scalars, I mean, there are going to be some similarities presumably, but I mean, but not. I mean, say if we do it, of course, for SYK, for instance, you have a full tower of fields in the bulk because the fermions are not free. Well, say if we do free fermions, then we'd really only get essentially one field in the bulk rather than this full tower of fields. I mean, so it's got to be in that sense simpler than SYK. But again, this is still a work in progress, so I'm not sure exactly what we'll get.
Nice.
Okay. The SYK model is not conformally invariant. It's not scale invariant. So you can do a bilocal formulation the way people have done. I mean, but I think one of your powerful points was that you're making a change of basis to a conformal basis.
Yes.
Which I don't know whether it can.
Which can be done also for the free scalars in 0 + 1 dimension, or for free fermions in 0 + 1 dimensions.
Yeah, that is true, but not for SYK. That's what I'm saying.
Yeah,
it's
right.
Not obvious. Okay. That's what I mean. Okay.
Yeah, of course. For SYK, I mean, you have to first go to this conformally invariant fixed point and work there.
Yeah,
that's
right. Yes.
Well, here would give us a simpler version of that story, where we should really be able to write the bulk action completely explicitly on this too. But this example, I think, would be more similar to the usual AdS CFT correspondence. I mean, again, here we just have fixed living on a fixed AdS background and so on. I mean, I'm not sure if we'd see any of this, say, dynamical boundary story that people see in the SYK and so on. I mean, but yeah, I don't know.
More questions? If not, let's thank Ofer again for a very nice talk.
Thank you very much.
Thank you.
Wonderful.
Okay, goodbye, everybody.
Bye-bye.
Bye-bye.